Alrighty, howdy folks. Let's look at section 2 of chapter 7, and this is with a few more identities that we are going to run into. Okay, addition and subtraction formulas, that's what it is called. So what's the motivation for this? Something like this. What is sine of a plus b? Right, the natural tendency would be to say, oh, that must be equal to sine a plus sine b, right? I mean, I wouldn't, if that's what you thought, I wouldn't blame you, because that's what most people reasonably think, that you can simply distribute the sine to a and b and write that as sine of sine a plus sine b. But the truth is that's not correct. Okay, certainly sine of a plus b is not equal to sine a plus sine b. The thing is, how do I know that? So one thing in mathematics that you can always do is, to prove something to be true is perhaps a little on the difficult side. However, sometimes to prove something is false actually becomes easy, and the way you do that is come up with a counter example. In the sense, sine of a plus b, is that equal to sine a plus sine b? To prove that to be wrong, that it is equal, I just need to come up with one example where that is not true, and then immediately you say, obviously that cannot be equal, right? So for that, what am I planning to do? Consider the following counterexample. Let's pick A to be some 60 degrees and B to be 30 degrees. Okay, I could have picked radian, but degrees. Okay. So what happens? A plus B therefore would be 90 degrees, right? So we are going to do something like this. First, we will evaluate the left-hand side sine of A plus B as sine of 90 degrees. And then we'll evaluate right-hand side as sine of 60 degrees plus sine of 30 degrees, sine A plus sine B, and see whether or not they are equal. Right? Sine of A plus B is sine of 90 degrees, and that's equal to 1. However, sine A plus sine B is sine 60 degrees plus sine 30 degrees, and we know that sine of 60 degrees, or sine of pi thirds, is square root of 3 over 2. And sine of 30 degrees, or sine of pi 6, is 1/2. So that's square root of 3 over 2 plus 1/2. Now the question is that equal to 1? Well, let's write like this. At least because the denominator is the same, we can add the numerators, right? So this is square root of 3 plus 1 over 2. Is that equal to 1? Answer is no. It is 3 plus 1 all over 2, which is 4 over 2 equals, that's going to be 2. Yeah. Had we had 3 plus 1, we would have had a 4. 4 divided by 2 would have been 2. So square root of 3 plus 1 over 2 is not equal to 1. Or maybe I could argue like this. Square root of 3 is about 1.732. 1.7, let us say. So 1.7 plus 1 is 2.7. Divide that by 2. What do you get? 2.7 divided by 2 is about 1.35. So certainly that's not equal to 1. Or if the top were to be square root, had the top been 1 plus 1 over 2, we would have had a 1. But this is not a 1. Therefore, this cannot be equal to 1. That's another way of arguing. Okay. More importantly, what did we demonstrate? We demonstrated that at least there is one case where sine of A plus B is not equal to sine A plus sine B. The moment you do that, that couldn't possibly be an identity. You cannot say, well, maybe that is not true for one case, but for every other case it is true. You cannot say that. Okay, so it is not an identity. Sine of A plus B equals sine A plus sine B. You just simply say, nope, that's not true. Okay, all right. Then the question becomes, what is it, right? In order to do that, we actually, believe it or not, try to find a formula for cosine of A minus B. Cosine of A minus B. What a fascinating thing, right? And after that, we'll come up with a formula for cosine of A plus B, and from that, we'll get sine of A minus B and sine of A plus B. Okay? Now, I can give you what this is equal to pretty right away, but I'm going to actually derive this, okay? And if you are interested, you can follow this along, but never in a test or a quiz will I ask you any question like this. Write the proof of cosine of A minus B equals whatever it is, or do all of this. So just follow along to get a sense of how mathematicians go about deriving certain things. It is fascinating. Okay, here is the idea. Suppose I have a circle with 1 as radius and origin at the center, which is what our favorite unit circle is all about. A circle with radius 1 and the origin, the center located at the origin. Let's say we have something like that, right? Then let's say we have an angle A like this. I have shown that to be obtuse in order to be for some kind of a clarity, but it doesn't have to be obtuse. It doesn't have to be in that second quadrant, but let's say I have some angle A. Cool. Now there is another maybe I should put that way. The moment I say that, would you agree that this point must have an coordinates of 1, 0, y1, because x is equal to, the radius is equal to 1, so the x value here must be 1. And the y value must be 0 because this point happens to fall on the x-axis, right? 1, 0 are the coordinates of this point. Then the question becomes, what are the coordinates of that point? What is cosine in terms of x, y, and r? X, y, and r, cosine is x over r, right? Cosine A is equal to x over r. But if r equals 1, what happens to cosine A? Cosine A equals x then, or x equals cosine A. Do you see the logic? So the x coordinate of this point is guaranteed to be cosine A. Okay, what about the what else do we know? We know that sine A is equal to y over r, right? If r equals 1, what do we have? So we have sine A equals y over 1, or sine A equals y, or y equals sine A. So that means the x coordinate of this point is cosine A and the y coordinate of this point is sine A. And that is true of any point on the unit circle. Its x coordinate would be cosine of the angle and the y coordinate would be the sine of the angle. All right, so keep that in mind. And so if I have another segment, line segment here, which makes an angle of B with respect to the positive x-axis, then again by the same argument I can claim that the x and y coordinates of that point on the unit circle must be cosine B and sine B. Are we clear about this? Cool. Now what? Would you agree that if all the way up to here is A, angle is A, and up to here is angle B, then the difference between these two, or this angle, must be A minus B, right? Here, without loss of generality, we are taking A to be bigger than B, and so this angle must be A minus B. Why am I saying A is bigger than B? Otherwise, I would have to use absolute value. Okay, now let's also look at something else. Let's look at the distance from this point to this point. Let's say that is some D. Cool. So, and the next thing I want to show you is, could we do this? What exactly did I do here? Knowing precisely what A minus B is, that is because you know what A is and what B is, which means you know angle A minus B, could we have constructed a segment which makes the same A minus B angle, but its initial side is actually coincident with the positive x-axis? So this is the initial side and that is the terminal side. In this case, this is the initial side and that is the terminal side of the angle A minus B. But we can transfer this and write like this, so that this is the initial side and that is the terminal side, but the angle is still the same, A minus B. Well, if that is the case, am I allowed to say that this distance must be equal to D just like this distance? Am I justified in making that claim? And the answer is yes. Why? Because this triangle and this triangle are congruent. How do I know that? I can prove that those two triangles must be congruent by using what is called the SAS postulate. What is that? Side angle side postulate. Now, take a look at this triangle. This side is the radius of the circle, which is equal to 1. Would you agree? And let's pick this one. This side is also this side is also has a length of 1 because that's the radius 1, right? So these two sides are congruent. Okay, and this side is congruent with this side because they are both equal to 1, the radius. And the angle between those two here is exactly the same as the angle between these two. So we have a side angle side equal to side angle side. That means by SAS postulate, these two triangles are congruent, not just similar, they are actually congruent. Oh, that means the corresponding sides must be identical. So this is D and that is also D. Whew. Cool? All right. So having made that argument, let's also do one more thing. Can you tell me what the coordinates of that point would be? X and Y coordinates. Well, do we know that point, that segment's angle with respect to the positive x-axis? Yeah, we know A minus B is that angle. So that means its x coordinate and y coordinate must be cosine of A minus B, comma sine of A minus B. Right? Okay, let's pause for a second. What in the world are we trying to do here? We are trying to find a formula for cosine of A minus B. And to do that, we had to do all this preparatory work. Okay, we did this. Now, how in the world are we going to get the formula for cosine of A minus B from this work? And the answer is, can we find the distance between these 2 points? The D? Do we know something called distance formula given coordinates x1, y1, x2, y2? What's the distance? Oh, the distance formula is square root of x1 minus x2 square plus y1 minus y2 square, right? So we will apply that since the distances are equal. So first, let's say cosine of A minus B, which is, let's think of that as x1, minus x2. x2 is this x coordinate, which is 1. So cosine of A minus B minus 1 would be x1 minus x2, the quantity square, plus y1 minus y2. y1 is sine of a minus b and y2 is just 0. So that is sine of a minus b, the quantity square. So if I put a square root on this one, that's how I would have d. I think I may have misspoken here. I said setting the distance as d equal. Actually, I'm setting the distance square equal so that I don't have to deal with the square root sign. Similarly, the distance from this point to this point is d here is x1 is cosine a, x2 is cosine b. So cosine a minus cosine b, the quantity square, plus sine a minus sine b, the quantity square. So I actually set the distance square equal. Okay. All right. So now it's a matter of just expanding out both the left hand side and the right hand side. Using the formula that a minus b, the quantity square, is a square minus 2ab plus b square. Would you agree? We would have cosine square of a minus b minus 2 times cosine of a minus b times 1, which is this, plus 1 square is plus 1. And then we have a sine square of a minus b. Cool? And what about the right hand side? Well, again, same formula. A minus b, the quantity square, is a square minus 2ab plus b square. And we can apply the same thing here, and this is what we get. Cosine square a minus 2 cosine a cosine b plus cosine square b plus sine square a minus 2 sine a sine b plus sine square b. So far, are we good? But then we notice something interesting here. Let's take a look at the left hand side. Do we have a cosine square of some angle plus sine square of the same angle? For a second, let's think of a minus b as theta. Do we have cosine square theta plus sine square theta? Isn't that equal to 1? Aha, so that means we can replace this cosine square of a minus b with a 1. And we have a 1 plus 1 equals 2. So the whole left hand side becomes 2 minus 2 cosine of a minus b. Okay, let's look at the right hand side. Cosine square a plus sine square a is 1. Similarly, cosine square b plus sine square b is 1. So we have a 1 plus 1 is 2. That's what I wrote here. And then we have a minus 2 cosine a cosine b minus 2 sine a sine b here. And now looking at this, what can we say? Hey, wait, there is a 2 here and there's a 2 here. If we subtract a 2 from both sides, they just disappear. And we end up with negative 2 cosine of a minus b is negative 2 cosine a cosine b minus 2 sine a sine b. Right? Or divide both sides by negative 2, we end up with cosine of a minus b is nothing but cosine a cosine b plus sine a sine b. Right? We derived that formula. Cosine of a minus b is cosine a cosine b plus sine a sine b. I'll come up with the formulas for cosine of a plus b, sine of a minus b, sine of a plus b, tangent of a minus b, tangent of a plus b, and all that. You would need to memorize that, but let's appreciate what we have here. All right, next. How do we find the formula for cosine of a plus b? Do we go through a similar process, draw? No. This is where mathematicians, you can tell, are very clever. Having gotten the formula for cosine of a minus b, they say, wait, you want a formula for cosine of a plus b? Think of that a plus b as a minus the angle negative b, right? Algebraically, you can do that. A plus b is the same as a minus negative b. Oh, okay. Now, does this look like cosine of a minus b? Yeah, of course, instead of a b, we have a negative b, but let's think of it as p minus q, cosine of p minus q. We have a formula for cosine of p minus q, so we apply that. So what does that give us? That gives us cosine A cosine of negative B plus sine A sine of negative B. But then one of the identities that we learned in the previous section was cosine of negative B is positive cosine B, whereas sine of negative B is negative sine B. So keeping that in mind, we got cosine A cosine B plus sine A times negative sine B, or becomes minus sine A sine B. All right. So cosine of A plus B is cosine A cosine B minus sine A sine B. All right. Okay. How do we find a formula for sine of A plus B then? Check this out. This is even different. The strategy here is, recall that cosine of 90 degrees minus theta is sine theta. You remember that co-function, sine and cosine are co-functions. That means cosine of 90 degrees minus theta is sine theta, sine of 90 degrees minus theta is cosine theta. Okay, let's see if we can make use of that. So sine of A plus B, I can write that as cosine of 90 degrees minus the quantity A plus B, right? That to me looks like sine theta is cosine of 90 degrees minus theta. Okay, where do we go from there? Oh, okay, we can redistribute. We can distribute and associate. We can use the associative property and say 90 degrees minus A minus B. We can write like that. So cosine of the quantity 90 degrees minus A minus B. Now, does this look like cosine of P minus Q to you? Yep. And so we can say that's cosine P, cosine Q plus sine P, sine Q. Or cosine of 90 degrees minus A times cosine of B plus sine of 90 degrees minus A, sine of B. Cool. All right. But what's up with cosine of 90 degrees minus A? What is that equal to? We already said this, right? The co-function identity, cosine of 90 degrees minus A is sine A. Similarly, sine of 90 degrees minus A is cosine A. So we can replace cosine of 90 degrees minus A with a sine A and sine of 90 degrees minus A with a cosine A. So we have sine A cosine B plus cosine A sine B. So ladies and gentlemen, what is sine of A plus B equal to? Sine A cosine B plus cosine A sine B. Okay, would you know how to get the sine of A minus B from this? Pretty much like this. Okay, sine of A minus B is sine of A plus negative B. And you do that, sine A cosine of negative B plus cosine A sine of negative B, and that gives you this formula. All right. And so let me summarize all of this. You must memorize these four formulas. You must. Cosine of A minus B is cosine A cosine B plus sine A sine B. Cosine of A plus B is cosine A cosine B minus sine A sine B. Sine of A plus B is sine A cosine B plus cosine A sine B. Sine of A minus B is equal to sine A cosine B minus cosine A sine B. You gotta be able to rattle that off that effortlessly. Okay, and not just remember it for this course. You will be using this quite a bit in calculus, differential equations, all kinds of places. Very important formulas. All right. Now, to find a formula for tangent of A plus B. Tangent of A plus B is certainly equal to sine of A plus B over cosine of A plus B. Would you agree with that? Yeah, that identity, tangent theta is sine theta over cosine theta. Instead of theta, we have A plus B. But we just derived formulas for sine of A plus B and cosine of A plus B. which is the top sine of a plus b, sine a cosine b plus cosine a sine b, whereas bottom cosine of a plus b is cosine a cosine b minus sine a sine b. Right? Cool. Well, we could stop there, and if you said tangent of a plus b is this, I guess nobody could question that. But then, look at a clever manipulation someone came up with sometime so that the formula actually looks much more elegant. Okay? And what somebody did long time back is they looked at this and said, wait, what would happen if I divide both the top and the bottom by cosine A cosine B? Right? Okay. Now you and I can certainly wonder, how in the world did they come up with that particular choice? Divide all the top and the bottom by cosine A cosine B. Why not sine A sine B? Why not sine? Right? Probably they tried it out and tried different ones, and this is the one that kind of looked elegant. Okay, where do we go from here? Now, am I allowed to write a plus b over c as a over c plus b over c? So I can write this as sine a cosine b over cosine a cosine b plus cosine a sine b over cosine a cosine b. Similarly, I can write the bottom also. So what would I end up with? Sine a cosine a cosine like this. And then we notice, hey, wait, I can cancel the cosine b's. Similarly, I can cancel the cosine a's here. And over here, whoa, both. So cosine a cosine b over cosine a cosine b, that's just 1. And I cannot cancel anything here. However, I can say sine a over cosine a is tangent a, sine b over cosine b is tangent b. Right? So let's recognize all of that. So what do we end up with? Sine a cosine a plus sine b over cosine b, 1 minus sine a sine b, and that's nothing but tangent a. This is nothing but tangent b. So we have tangent a plus tangent b over 1 minus tangent a tangent b. So with a drum roll, let's announce tangent of a plus b equals tangent a plus tangent b over 1 minus tangent a tangent b. Would you agree that that's a lot more elegant than this? This is also something that you need to memorize. You do not have to memorize cotangent of a plus b or secant of a plus b or any of that stuff. As long as you remember for sine, cosine, and tangent, we are good. And what's up with tangent of a minus b? In the top, you'll have a negative. You will have a subtraction. And in the bottom, you will have a addition. That's the difference between tangent of a plus b and tangent of a minus b. Cool? All right. So with that, I think, the question might be, why do we need these formulas? We need these formulas. One reason we need these formulas is we can now find the exact values of a few other angles. Up until now, we knew for 0, 30, 45, 60, 90, right? The exact trig ratios for those angles. This allows us to find for a few other ones. For instance, can we figure out what sine of 15 degrees is? Right? The answer is, maybe I'll put that as in the form of a question. Can you pause the video and think of, from the stuff that we learned right now, can we figure out how to find sine of 15 degrees? Could we write 15 as 45 minus 30? What? 15, is that the same as 45 minus 30? Yeah. Or 60 minus 45? Yeah, that's also a possibility. So we will write sine of 15 degrees as sine of 45 degrees minus 30 degrees. And then we go, aha, that's looking like sine of A minus B. And what's the formula for sine of A minus B? Sine A cosine B minus cosine A sine B. So that means this is going to be sine of 45 degrees cosine of 30 degrees minus cosine of 45 degrees sine of 30 degrees. Cool? All right. How do we know all these values? Yeah, sine of 45 degrees is square root of 2 over 2. Cosine of 30 degrees is square root of 3 over 2. And cosine of 45 degrees is square root of 2 over 2. Sine 30 degrees is 1/2. And we just plug and chug. And so that gives us square root of 6 over 4 minus square root of 2 over 4. And we can combine that and write as square root of 6 minus square root of 2 over 4. Right? That's good enough. So here we have found the trig function value of another angle, 15 degrees. That's one of the things. That's one of the advantages of all deriving these new formulas. Okay. What about cosine of 105 degrees? Well, could we write 105 as 45 degrees plus 60 degrees? And so cosine of A plus B is cosine A cosine B minus sine A sine B. Every time you solve such problems, just repeat to yourself, that's cosine of A plus B. What's the formula? Cosine A cosine B minus sine A sine B. The more you repeat, the better it gets entrenched in your memory. Okay? So cosine 45 cosine 60, sine minus sine 45 sine 60. Let's do the same thing. And this turns out to be square root of 2 minus square root of 6 over 4. Cool? This turns out to be the negative of that value. Coincidence? I think not. Right? What's a good argument for that? Cosine of okay, maybe I'll put it this way. Cosine of 90 minus theta is sine theta, right? Cosine of 90 minus theta is sine theta, the cofunction identity. So cosine of 90 minus 105 must be sine of 105 degrees. What is that? Sine of 90 minus 105. Cosine of 9. Man, why am I struggling with this? Yeah, I think it's much easier this way. The cofunction formula works this way as well. Cosine of 90 plus theta, okay, earlier we had a formula for cosine of 90 minus theta as being equal to sine theta. From that you can actually derive that cosine of 90 plus theta is sine theta. However, with a negative. Why would it have a negative? Because 105 happens to be in the second quadrant, so we attach a negative to it. So cosine of 90 plus theta is actually negative sine theta. So we can look at cosine of 105 as cosine of 90 plus 15, and so that should be equal to negative sine 15. So sine 15, we got this, so this should be negative of that, and that's why we have this. Man, I had to think about it for a second. All right, problem. Whoa, Nelly. How do we deal with this one? What looks complicated actually is not so complicated when we pay attention. What is that? This is cosine A cosine B plus sine A sine B. Right? Cosine A cosine B plus sine A sine B. Wait, that's equal to cosine of A minus B. Yep. So if we recognize that, we can simply say this whole big long thing must simply be equal to cosine of 3 pi over 7 minus 2 pi over 21. Right? Now it's a matter of subtracting these two fractions. The common denominator is 21, and so this is 9 pi minus 2 pi over 21, and that is cosine of 7 pi over 21. But 7 goes into 21 3 times, so that's just cosine of pi thirds. Cosine of pi thirds is cosine of 60 degrees, which is 1/2. See that? Okay. What else? Prove the identity that sine of x minus pi equals negative sine x. Sine of x minus pi is negative sine x. Left hand side is sine of x minus pi, and we can immediately say that looks like sine of a minus b, which is sine a cosine b minus cosine a sine b. So let's use that and write this as sine x cosine pi minus cosine x sine pi. Cosine pi is negative 1. Sine pi is 0. Right? So we can say cosine pi is negative 1, sine pi is 0, and so this becomes negative sine x minus 0, which is negative sine x. That's the right hand side. Cool. Now, just a while ago I talked about a cofunction identity. Cosine of 90 plus theta is equal to negative sine theta. Can you prove that identity for yourself in the same way? Cosine of 90 degrees plus theta, that is cosine of a plus b. That's in the form of cosine of a plus b. So cosine 90 cosine theta minus sine 90 sine theta. If you do that, you will clearly see that cosine of 90 plus theta is negative sine theta, like I said. Okay, prove the identity tangent x minus tangent y is equal to sine of x minus y over cosine x cosine y. Whoa. Okay. To me, the simple strategy would be to take the right hand side and work with it. So that's equal to sine of x minus y over cosine x cosine y. So that makes it sine x cosine y minus cosine x sine y over cosine x cosine y. And now, to me, this looks like a minus b over c, which is a over c minus b over c. So let's separate out the fractions, and cosine y's cancel, cosine x's cancel in this one, leaving us with sine x over cosine x minus sine y over cosine y, which we recognize as being tangent x minus tangent y. That's the left hand side. Done. Cool. Write the expression in terms of x and y only. Ooh. Of what? cosine of sine inverse x minus tan inverse of y. Very important problems. Okay, cosine of sine inverse x minus cosine of the quantity sine inverse x minus tan inverse y. Okay, let's say sine inverse x, let sine inverse x equals alpha, right? And so sine alpha must be equal to x. Similarly, the moment we have that, we can draw the triangle. First quadrant is perfectly fine. Sine alpha equals x, knowing that, let's draw a triangle, right triangle, and label this angle as alpha. And x means x over 1. So the opposite is x, and the hypotenuse is 1. You better remember this really well, this whole process, because this is something that will be very useful in what's called trig substitution in calculus 2 while evaluating integrals. When we have sine alpha equals x, we draw a triangle, right triangle, and label one of the angles, the non-90 degree angles, as alpha, and then we say, wait, that's sine alpha is opposite over hypotenuse, so the opposite must be x and the hypotenuse must be 1. So what should the other leg be? By Pythagoras theorem, square root of 1 minus x squared, right? Cool. So let's keep that in mind. And similarly, tan inverse of y, let's call that as beta. So tan inverse of y is beta, and tangent of beta therefore must be equal to y. Armed with this piece of information that tangent of beta is equal to y, let's construct another right triangle and do a similar thing. Tangent is opposite over adjacent, so that means the opposite must be y and adjacent must be 1. And from the Pythagoras theorem, the unknown side, which is hypotenuse in this case, must be square root of 1 plus y squared. So we got this and this. So the question is, how is that going to help us figure out cosine of sine inverse x minus tan inverse y? Right? Check this out. I think the first time I ever saw it, I was like, dang, that is pretty smart. We ourselves let sine inverse x be equal to alpha and tan inverse y equals beta. So could we replace this sine inverse x with a simple alpha and replace tan inverse y with a simple beta? Yeah, we can. So that's simply reduced to cosine of alpha minus beta. Why, man? What's the big deal about that? Well, the big deal about that is, now this is looking like cosine of a minus b. We can apply our identity and write this as cosine alpha cosine beta plus sine alpha sine beta. Right? Okay. Now, let's pause here for a second and ask, what exactly is the problem asking us to do? It's asking us to write this expression in terms of x and y only. Apparently, there should not be any sines, cosines, or anything like that. It's just x's and y's. Constants are okay. Are we in a position to do something like that? Expressing this whole thing now in terms of just x's and y's? Yeah, we are. This is cosine alpha times cosine beta, right? Can we go to the triangle and now figure out what cosine alpha is? Yeah, cosine alpha is adjacent over hypotenuse. Adjacent happens to be square root of 1 minus x squared. Hypotenuse happens to be 1. Cosine beta is 1 over square root of 1 plus y squared. And similarly, sine alpha is opposite over hypotenuse, x over 1. Sine beta is y over square root of 1 plus y squared. We figured those things out and we'll plug. Right? Cosine alpha is square root of 1 minus x squared over 1, which I wrote as just simply square root of 1 minus x squared. and cosine beta is 1 over square root of 1 plus y square, x over 1, y over square root of 1 plus y square, right? We'll write that slightly more elegantly. Recognizing that the denominators are the same, we can multiply and then add the fractions, add the tops, and that gives us square root of 1 minus x squared. Goofed. I am sorry. There should be an xy. Plus xy over square root of 1 plus y squared. Cool. Oh man. Will I ever become infallible? I don't think so. That's fine. I like to be a fallible human being. Where are we now? Problem. Find the exact value of the expression. Sine of cosine inverse of square root of 3 over 2 minus tan inverse of 1. Exact value of the expression. Sine of... Does that kind of look like, sort of resemble the previous one? Write the expression in terms of cosine of some inverse x minus some other inverse x. This kind of like that. Sine of cosine inverse of something minus tan inverse of something. Well, there are two ways of solving this problem. Method 1. We'll adopt a similar strategy as the previous one. That is, we'll say let cosine inverse of square root of 3 over 2 be equal to alpha. And that implies cosine alpha must be square root of 3 over 2. So we'll draw a triangle, right triangle for ourselves, and say alpha, cosine is adjacent over hypotenuse, so adjacent is square root of 3, the hypotenuse is 2, and so by Pythagoras theorem this should be 1. Similarly, tan inverse of 1, let's set that equal to beta, and then tan beta is equal to 1, and let's draw this, and the hypotenuse would be square root of 1 square plus 1 square is square root of 2. Cool. So sine of this becomes simply sine of, this whole thing can be replaced by alpha, the whole tan inverse of 1 can be replaced by beta, so sine of alpha minus beta, which is sine alpha cosine beta minus cosine alpha sine beta. Now the question is, do we know the value of sine alpha? Well, if you don't, come to this triangle and use that to figure out sine alpha. Sine alpha is opposite over hypotenuse, 1 over 2. Cosine beta is 1 over square root of 2. Cosine alpha, square root of 3 over 2. Sine of beta, 1 over square root of 2. Plug and chug. And both the denominators is 2 square root of 2. So we can just subtract the tops. And that just gives us 1 minus square root of 3 all over 2 square root of 2. Right? That's one method. And in fact, this is more of a generic method. Even if we didn't have cosine inverse of square root of 3 over 2, say we had something like cosine inverse of, 3/5 minus tan inverse of 5/12, something like that, we could have adopted the same procedure. But because there is something about cosine inverse of square root of 3 over 2 and tan inverse of 1, we actually know the exact values of those things. We can do we can take a different approach and solve this problem. What is cosine inverse of square root of 3 over 2? In other words, cosine of what angle in 0 to pi gives us square root of 3 over 2? Square root of 3 over 2, that's cosine of 30 degrees. So cosine of pi 6 is square root of 3 over 2. So cosine inverse of square root of 3 over 2 is just pi over 6. Tan inverse of 1, we know the tangent of 45 degrees is 1, or tangent of pi fourths is 1. So tan inverse of 1 is pi fourths. So let's replace by those exact values. Sine of pi over 6 minus pi over 4. Well, subtract the fractions now. Ooh, I didn't do that. Yeah. Subtracting the fractions is not a good idea. This is better. So now let's look at this. Sine of pi 6 cosine of pi 4s minus cosine of pi 6 sine of pi 4s. Basically applied sine of a minus b sine a cosine b minus cosine a sine b. And when we do that, sine pi 6 is sine 30 degrees is 1/2. Cosine pi 4 is square root of 2 over 2. Cosine pi 6 is cosine 30 degrees is square root of 3 over 2. And this is square root of 2 over 2. And we get exactly the same as this guy. Right? That's another way. Cool? All right. Slide 9 of 9. Find the exact value of the expression tangent of theta plus alpha. Exact value of the expression given. Cosine theta is negative 1/3. Theta is in quadrant 3. Sine alpha is 1/4. And alpha is in quadrant 2. Well, this should be kind of similar to the previous problems, except where we draw the triangle kind of changes. That's the only difference. Okay. So, cosine theta is negative 1/3. And theta must be in Q3. So, certainly, I decided to draw this in Q3. And cosine is, in terms of x, y, and r, is x over r. So x must be negative 1 and r must be 3. And then by Pythagoras theorem, this side should be plus or minus square root of 8. But since this is in the third quadrant, y coordinate must be negative. So we choose negative square root of 8. How do we get that? I said 3 square minus the quantity negative 1 square. So 3 square minus 1. 9 minus 1 is 8. And so square root of 8 plus or minus, we pick negative square root of 8 because in the third quadrant. Similarly, let's draw one for sine alpha. That happens to be in Q2. And in terms of x, y, and r, sine is y over r. So that means y must be positive 1, r must be positive 4. However, the x must be negative because we are in the second quadrant. So 16 minus 1 is 15. Plus or minus square root of 15. We choose the negative square root of 15. Cool? Would you agree that this is somewhat similar to what we did in the previous case? There, our triangles, we just simply drew this regular right triangle and worked with it. We didn't have to worry about the quadrants. So by default, we just simply took it to be in the first quadrant. However, here, since we are being forced to use the quadrant system, we accede to their request and do this. Okay, now where do we go from here? So tangent of theta plus alpha. What's tangent of a plus b? Tangent a plus tangent b over 1 minus tangent a tangent b. So that's exactly what I did here. Now, do we know how to find tangent theta? Yep, go to this triangle and ask it. Tangent in terms of x, y, and r is just y over x. That is negative square root of 8 over negative 1, or just simply square root of 8. Tangent alpha, y over x, 1 over negative square root of 15. So those are the values I just simply plugged. So it's a matter of now doing some simple algebra. Are you okay with this thing? Square root of 8 over 1. And so that just simply becomes square root of 15 square root of 8 minus 1 over square root of 15. Similarly, 1 plus square root of 8 over 15. Oh, goofed. Samuel. Come on, come on, come on. That ain't just that should be square root of 15. Yep, square root of 15 plus square root of 8. So this is going to be square root of 15 plus square root of 8. Yep. Brother. That was not on the numerator. It was this 1 plus the quantity square root of 8 over square root of 15. And so, yeah. All right. I think that's about it. Alrighty. Let's make sure that you work a lot of problems based on this